welcome to lecture series on advanced linear algebra. We have already learned in inner product space, if a linearly independent set of vectors are given over a vector space, that is also inner product space, then one can have corresponding a set of orthogonal vectors. This has been proved by construction by Gram-Schmidt orthogonal procedures. In that construction procedure, we have adopted a principle, a geometrical concept which is called basically orthogonal projection. Repeatedly we have used that one. This concept will be more clear, and this concept is most important in approximation theorems, we will see soon. But before that, let me define what is the meaning of best approximation of a vector over a subspace of that vector space. So, this concept let me introduce like this. Let V be an inner product space I.P.S. over a field either real or complex, that is my capital F. Let W be a subspace of V. Let beta belongs to V be any element. The best approximation of beta by the vectors W or best approximation of beta in W is an element alpha belongs to V such that norm of beta minus alpha will be less than or equal to norm of beta minus gamma for all gamma belongs to W. So, alpha is said to be best approximation to beta over this subspace W provided norm of beta minus alpha is less than or equal to norm of beta minus gamma, please. Now, if I go to 11-12 concept and go to this, say our over the space R3 with standard inner product on R3, let V is equal to R3 with standard inner product in R3, and if I consider, say this is my say x axis, y axis and z axis. Now, over this Euclidean space, if I take a point, say this is a point P having coordinates say x comma y comma z, and when you are talking the best approximation by the vectors over the xy plane, what I see that we used to project this vector over the xy plane. Suppose it is here, this vector that is basically having say P prime, coordinate will be x comma y comma z. So, we see that suppose this is the alpha and this is your beta. then I see that this is the vector beta. So, you see that beta minus alpha, which is equal to this one, p prime to p is beta minus alpha, p prime to p is a orthogonal or perpendicular to the xy plane. So, let us think then the best approximation of any vector in R3, say P having coordinate x comma y comma z in xy plane is P prime, which is having coordinate x comma y comma 0. Okay. And so, suppose if I denote is equal to alpha and this is my beta equal to p, then beta minus alpha is orthogonal to xy plane, that is beta minus alpha is orthogonal to any vector in xy plane. Now, whether this concept is valid for more than 3 dimensional or not. So, now you can see this concept will remain valid for finite dimensional vector space, that if alpha is the best approximation to the vector beta, then beta minus alpha will be orthogonal to the any element of W. Okay. This concept will remain valid for the finite dimensional space, but for the infinite dimensional space it may not, because in that case the existence of best approximation also questionable please in some cases. So, and we need a special treatment for to understand to prove this concept. So, now we will talk in nice results which will talk about the best approximation of any vector beta on V with respect to a given subspace W of V. This is like this in terms of theorem I am writing it. Let V be an inner product space. I am not saying the dimension of V is finite or infinite, nothing. I am saying V is an inner product space. Let W be a subspace of it. Let beta belongs to V be any element. Then okay, then the vector alpha in W is the best approximation of beta if and only if beta minus alpha is orthogonal to each vector in W. Second, if the best approximation of beta exists, then it is unique. Third, if dimension of W is finite and alpha 1, alpha 2, alpha n is an orthogonal basis for W, then alpha equal to sigma beta alpha k, inner product of beta alpha k by norm of alpha k square into alpha k, k equal to 1 to n, and it is unique. It is unique, please. So, let us talk about the proof of this interesting results. So, what is the theorem says? Theorem says that if V be an inner product space, the space may be finite dimensional, may be infinite dimensional, and if W be a subspace of V, here also W may be finite, may be infinite dimensional subspace, and we picked up beta be any element of V. The first point is saying that the vector alpha in W is said to be the best approximation to beta with respect to W if and only if the vector beta minus alpha is orthogonal to each vector in W. So, for this we do not put any restriction that whether W is a finite dimensional or infinite dimensional. Second is, if the best approximations of beta in W exist, then has to be unique. So, here also we do not need that whether W has to be finite dimensional or infinite dimensional. In third point, if the W is a finite dimensional vector space and alpha 1, alpha 2, alpha n an orthogonal basis for the space subspace W, then the best approximation to beta, which is given by alpha, that can be written as summation of inner product of beta alpha k divided by norm of alpha k square times alpha k, k equal to 1 to n. Okay, so let me prove the first part. So, we know if alpha is best approximations to beta implies norm of beta minus alpha has to be less than or equal to norm of beta minus gamma for any gamma belongs to your W, please. So, we have to show, okay. So, this is known to given to us, please. Now, this definition is known. Now, is saying that if beta minus alpha is orthogonal to each vector in W, I have to show that alpha is the best approximation to beta. So, now let me prove the if part, please. Given your beta minus alpha is orthogonal to each vector in W. It is given to us. We have to prove that norm of beta minus gamma will be greater than or equal to norm of beta minus alpha for all gamma belongs to W. We have norm of beta minus gamma, norm of beta minus gamma whole square equal to, one can write norm of beta minus alpha plus alpha minus gamma whole square. Okay, for gamma belongs to W. So, this implies norm of beta minus gamma whole square equal to norm of beta minus alpha whole square plus norm of alpha minus gamma whole square plus 2 times of real component of inner product of beta minus alpha and alpha minus gamma. Already we have learned that norm of beta minus alpha plus alpha minus gamma whole square equal to can be written like this thing, that is using the standard definition of the inner product please. Now, since beta minus alpha is orthogonal to alpha minus gamma, so this means that inner product of this quantity has to be equal to 0. So, this implies norm of beta minus gamma whole square equal to norm of beta minus alpha whole square plus norm of alpha minus gamma whole square. So, in the right hand side both the terms are positive quantity please. So, this implies that norm of beta minus gamma whole square is greater than or equal to norm of beta minus alpha whole square, okay, for all gamma belongs to W. This implies norm of beta minus gamma is greater than or equal to norm of beta minus alpha for all gamma below this one. So, this implies that alpha is the best approximation to beta, is the best approximation to beta please. Okay. Now, let us go for the only part please, that is this one please. So, here it is given alpha is the best approximations to beta. So, this implies norm of beta minus gamma whole square is greater than or equal to norm of beta minus alpha whole square for all gamma belongs to W, it is given to us. So, this implies we know according to star we have norm of beta minus alpha whole square plus norm of alpha minus gamma whole square plus 2 times of real inner product of beta minus alpha and alpha minus gamma. So, this quantity is greater than or equal to norm of beta minus alpha whole square. So, this implies that norm of alpha minus gamma whole square plus 2 times of real component of inner product of beta minus alpha and alpha minus gamma is greater than or equal to 0. So, this is true for all gamma belongs to W please. Since W is a subspace of vector space V. So, this implies that each element of W can be expressed in the form of alpha minus gamma, please. I mean, if you picked up any element say t, then one can write down t, if alpha belongs to W, then one can write down your that alpha minus t type. So, one can write down this form please. So, let alpha minus gamma, if I represent some vector r belongs to W, our last result says that, so we have norm of r square, norm of r whole square plus 2 times of real component of inner product of beta minus alpha and r is greater than equal to 0. So, this is true for any r belongs to W. So, in particular for r equal to, when I consider r equal to minus inner product of beta minus alpha and alpha minus gamma divided by alpha minus gamma in whole square and alpha minus gamma, this vector. So, if I have taken a particular r equal to this type of structure please. So, this belongs to also W, then results, this is suppose double star, so double star still holds good for even for this r. So, this implies that if I substitute it, what I am getting? I am getting here norm of r square, inner product of this and this. So, inner product of, so I will have inner product of minus beta minus alpha and alpha minus gamma, this divided by alpha minus gamma a whole square and alpha minus gamma, this vector. Okay. So, this and minus inner product of again beta minus alpha and alpha minus gamma divided by alpha minus gamma a whole square and alpha minus gamma. Okay. So, norm of r square equal to inner product of these two vectors, I mean this one, plus 2 times of real component of again beta minus alpha and r is greater than equal to 0. So, if I simplify this ones, this implies that I will have minus into minus plus. So, I will have mod of beta minus alpha and alpha minus gamma inner product of this a whole square. Okay. So, this will be this one, if we take it this side, then conjugate bar will come to that side. So, total will be mod of beta minus alpha, inner product of beta minus alpha and alpha minus gamma a whole square divided by norm of alpha minus gamma to the power 4 and here again inner product of alpha minus gamma, alpha minus gamma. So, this will be there minus 2 times, even if I take real for time being, let me write down real, no problem. So, I will have inner product of beta minus alpha and here I will have inner product of beta minus alpha, alpha minus gamma divided by norm of alpha minus gamma whole square and the vector alpha minus gamma. So, this one. So, this is also greater than equal to 0. So, this implies I will have mod of inner product of beta minus alpha, alpha minus gamma এর whole square divided by norm of alpha minus gamma এর whole square, and this side minus, since if I take it again this side bar will come to the pictures, and I will have this one and okay. So, it will be again minus 2 times mod of inner product of beta minus alpha and alpha minus gamma a whole square will come to the picture divided by norm of alpha minus gamma a whole square, and then yeah. So, this will be like this, and this is a positive quantity. So, real number only. So, real RE component is basically real part means is basically real number. So, it will be I can write simply minus 2 times of mod of inner product of beta minus alpha and alpha minus gamma whole square divided by alpha gamma whole square. So, this is also greater than or equal to 0. So, this implies negative of positive quantity beta minus alpha and alpha minus gamma, this whole square is greater than or equal to 0. A positive number is greater than or equal to 0 implies that your certainly beta minus alpha is orthogonal to alpha minus gamma. So, we see that if alpha is the best approximation to beta, then beta minus alpha is orthogonal to alpha minus gamma. In fact, it is orthogonal to every vectors in W, because each vector in W we have already explained that it can be written as alpha minus gamma also in this form. So, we see that if beta minus alpha is orthogonal to every vector W. The second one, that if beta a best approximation to beta in W exists, that has to be unique, and this proof it is very straightforward also. Okay. Let if possible the best approximation to beta in W, say alpha 1 and alpha 2, where alpha 1 not equal to alpha 2 and alpha 1 belongs to W, alpha 2 belongs to W. We have to show that alpha 1 equal to alpha 2. See, since alpha 1 is best approximation to beta, implies that norm of beta minus alpha 1 will be less than or equal to norm of beta minus gamma for all gamma belongs to W. Okay. So, this implies norm of beta minus alpha 1 can be written beta minus alpha 2 and plus alpha 2 minus alpha 1 will be less than or equal to this quantity. But we have norm of beta minus alpha 1 square equal to norm of beta minus alpha 2 square plus norm of alpha 2 minus alpha 1 square plus 2 times of real part of the beta minus alpha 2 and alpha 2 minus alpha 1. So, this component has to be 0, because alpha 2 and alpha 1 belongs to W and beta minus alpha 2 is orthogonal to any element of W. So, alpha 2 minus alpha 1, and since alpha 2 is also best approximation to beta, so this has to be 0, they are orthogonal, so this is 0. So, this implies this quantity is greater than equal to norm of beta minus alpha 2 whole square. Okay. And if alpha 2 not equal to alpha 1, so in fact I will say that it is strictly greater than this quantity, please, for alpha 2 not equal to alpha 1. Similarly, we can show that norm of beta minus alpha 2 whole square is strictly greater than norm of beta minus alpha 1 whole square. It is the same concept, please. So, this two will contradict. So, this implies that norm of beta minus alpha 2 will be equal to norm of beta minus alpha 1, and it is possible when norm of alpha 2 minus alpha 1 equal to 0. So, this implies alpha 2 equal to alpha 1. The third one, it is given to us, given W is spanned by order basis consisting of orthogonal vector, number is finite. So, spanned by alpha 1 to alpha n, okay, which are orthogonal. Okay. We have now for alpha equal to sigma, for alpha equal to sigma inner product of beta alpha k by norm of alpha k square and alpha k equal to 1 to n, we have beta minus alpha is orthogonal to each vector alpha k equal to 1 to n. This is basically which is coming as a consequence of our Gram-Schmidt orthogonalization procedure. We have already checked that beta equal to alpha, beta is equal to, if I consider that beta minus sigma k equal to 1 to n this quantity, this vector, if I denote say it is a gamma, then gamma will be orthogonal to each vector of alpha k. So, that is why I can say beta minus alpha is orthogonal to each vector alpha k equal to 1, which is we have already seen. We have already proved in Gram-Schmidt orthogonalization procedure. So, this implies that beta minus alpha is orthogonal to each vector in W, because W is spanned by this one. So, according to our first results, to 1, alpha is the best approximation to beta with respect to elements of W. And since the way alpha has been constructed or defined here, so the coefficient is, since the coefficient in the expression of alpha, alpha is say beta and alpha k by norm of alpha k square. So, implies alpha is unique. If you say any other vector, then definitely that vector will also have coefficient of alpha k will be exactly beta minus alpha k, beta inner product of beta alpha k divided by norm of alpha k square. So, therefore, I can say that this alpha is unique. So, we will discuss more and in our next class, but before completing this class let me give an examples. Consider V is equal to our Euclidean space R3 equate with standard inner product. So, the inner product space V is equal to R3 I have considered, that is our standard inner product space in Euclidean space please. Okay. So, let me consider the problem like this: V is equal to R3, that is our 3 dimensional space, Euclidean space, and the inner product in this space is our standard inner product. And suppose I have to get the best approximation of elements, say beta equal to say minus 10 to 8, and this best approximation with respect to subspace W, which is spanned by 3, 12 minus 1 by the vector 3, 12 minus 1. So, in this case so I have to then according to the last theorems, the best approximation of beta on W is say alpha, which is equal to inner product of beta and the basis element of W, that is 3, 12 minus 1, norm of this 3, 12 minus 1, this vector whole square, and 3, 12 minus 1. Since the dimension of the space W is 1, so the best approximation of beta on W will be alpha of this form please. So, this is will be equal to, you have given me the beta. So, inner product of 10 to 8 and 3, 12 minus 1, this divided by inner product of this one 9 plus 9 plus 144 plus 1, right. So, yeah, so some number will be there, and then 3 comma 12 comma minus 1 please. So, this will be equal to minus 30 plus 24. I am just telling you the procedure please. So, this is the number divided by this is 10 154, okay, and into the vector 3 12 minus 1 please. So, this is the answer please. So, we will continue the concept of best approximations over the inner product space V in our next class also please.